So thanks everybody for joining us here on November 11th, Veterans Day. And we have an exciting talk here by Gustavo, who, update me, you are master's or PhD student?
I'm a PhD student.
Okay, cool. I always lose track of that with some of you, but
it's okay.
Here to talk to us about the latest piece of hardware from Virginia Tech that I think it might be the next one if LACE doesn't go up before it. I think it'll be the next piece of VT hardware to go to space. So and it's, as you can see on the screen, VT ThickSat. So without further ado, I'll turn it over to you, to Gustavo.
Thanks, Lauren. Hi, my name is Gustavo Gargioni. I'm a PhD candidate here at Virginia Tech on the Aerospace and Engineering, Aerospace and Ocean Engineering Department. I'm here to talk about the ThickSat. It was an effort to build, manufacture, assemble, and build this satellite for the last year and a half. And then it is about like 2 weeks now that we have delivered, or 2 weeks maybe, that we have delivered to NSL to then fully integrate on the rocket launch. Launch should be going, we'll take a ride in the NG-15 launch in NASA Wallops launch facility, as we'll go aboard the Antares rocket with Cygnus resupply mission, and it will be delivered to space before reaching the ISS on its way up there. So let's start. So let's talk a little bit about the mission. This presentation is my full technical presentation on this development, mainly because we were working actually on building the hardware. So it only took me like a couple of weeks to put everything together. Hopefully it's not gonna be boring. I haven't did any script for this presentation, but it should be, I'll try to be at around 35 minutes, 40 minutes. If I need to run a little bit, I'll try to do as best as I can to run a little bit. Should be around 30 slides to finish it. So we'll start talking about the mission and how it all started, some history and acknowledgements. So first of all, this was an effort by undergrad students who make their capstone design group and the student design project into trying to assess the technicality of deploying a carbon fiber boom in space, which is this guy here. So this carbon fiber, it's interesting because once you open it up, it tries to create some kind of like structural resistance. As you can see here on this projected image, they have some structural, give some structural basis for the solar sail. And this is actually a NASA mission. It's called the ACS-3 mission. It's going, it's already built. We can see here in the payload. And it's about a 12U, and it's going to launch on the Artemis 1 mission aboard the SLS. Yeah. So the idea is that, okay, so why don't we give some extra assessment on this technology for NASA, and we can launch before in a smaller payload to test how well this boom can behave in space, right? So then Dr. Black and Dr. Shimpakri sponsor all this mission alongside with partners and other companies. So mainly Virginia Space and SL and TWIX, who have a consortium around the ThinSat program. And then of course, Virginia Tech, NASA, who provides us the boom for the students to create their payload. So, and then under this, they created a need, which was to design a payload to test deployment confirmation of the high strength composite boom, giving some constraints on the ThinSat program. So the ThinSat has some constraints on like volume, mass, and power budget and data transmission. And also some alterables, which is what the students can vary on their spacecraft as sort of like a confirmation assessment for the deployment of the moon, where they actually selected an image system and in a shaft tick counter to both confirm that the boom can be deployed in space. So what is the ThinSat? So the ThinSat is a program, like I said, designed by the NSL and Twigs and Virginia Space, where they slice a CubeSat into multiple pieces, like this Brad set, like Brad stylish piece that we call 1T. And if you stack 6 of them together, it is roughly a size of like 1 U unit. And the way that they deliver this in space is that all these 3 companies buy a 3U CubeSat slot, and then they deploy all these same sets together, stacked one over the other. Now, one key information is that for the ThickSat, we all created a payload that is the size of 60, so it's the size of 6 of these stacked together. And then in the end, the chassis solution provided by this mission now opens the opportunity for flexible size small satellites. So the chassis and the knowledge surrounding how to make this happen now can provide Virginia Tech and future missions to use either 2Ts or 20Ts. In some way, anything between 1T and 3U, we can work around. So like I said before, this was a capstone design. These are the people involved on the development of the first version of the ThickSat that is called the BradSat and was presented as a senior design. This is their design. You can see here there is a 1T in silver and a 5T chassis where they put the payload, their spool, and the spring that contains this spool. And then upon opening the door here, the boom will release itself, transforming some string energy, potential energy into kinetic energy. And then they put some cameras to then confirm and transmit data. And their idea was to use a Raspberry Pi to operate the software and communicate with the ThinSat, and then actually transmit the data through the ThinSat. And then this was fall 18 and through the beginning of summer 19, where me and my buddies, we picked up the project and then we delivered by a few weeks ago. So mainly these are the team involved. It's a bunch of like grad students and undergrads. Some of them are failed to do the tasks. So I had them here as just some among us icons. Yeah, and then it's important to know that 7 of these members on this team had experience with delivering the VCC, which was the CubeSat project that we delivered before the ThickSat. Okay, so the first thing that we did on summer 19 was do a spacecraft design assessment from the senior design team. So, so in the verge of all members of RadSat will be graduating. Basically, we needed to start a new team from the start. So Dr. Black requested us to complete the development, assembly, and delivering the project within the project deadline. So a few challenges on this assessment was that none of us were familiar with the mission, neither the boom itself and its objective. Some of us were graduating, like Seth was finalizing his dissertation. And some of the mechanisms were not fully developed or evaluated on their design. This was the first ThinSat mission that Virginia Tech ever took. to do, and there was some uncertainties regarding if it was going to be like a more balloon effort flight, or it was going to be like a space flight hardware, or which one should we be focusing for the summer. So technically, some critical design overviews and concerns were that there was no developed software or architectural design for the software yet. There was no all these door mechanisms that we see here. The first one that holds the boom, and the second one that opens the camera. These were not mechanisms that were developed by the team, so this was overdue. The release of the spool itself created, it was still creating some blooming. So blooming is when the tape spring it's holding its potential, and when it wants to release itself, it goes in all directions. And we need to confirm all this energy to go into one direction so we can have like a successful deployment. And we were having a lot of blooming on this design. The chassis itself had a complex manufacturing design, so we were caught in surprise in this design. It was very complicated to manufacture as a single piece, especially, and then this needed to do some rework here, and there was no development for the magnetic sensor. So the team created requirements for taking an image and also counting the ticks on the spool itself to transmit, okay, so how many rotations the spool did while deploying the boom. And their idea was to create some magnetic on the side here to count how many revolutions the spool did, and there was no development on it. So then we start summer with the goal of developing our Block 1 satellite. So the first thing that we did was to change to subsystem teams based on expertise instead of based on desire. So basically, we had a great deal of experts in our team. Derek was a mechanical expert. Minton is an ace on manufacturing materials. Rob had previously worked on boom mechanisms, and Saf was a mastermind of software. We had Hove, which was his apprentice. And basically what we did was like, okay, so which one has more expertise in what? And we tried to focus that expertise directly to the subsystem that did it most. We also changed to rapid prototyping design, which basically comprised of like 3D printing parts, putting up to test, and then refeeding all the tests backwards to a new prototype. And we're doing this in a weekly basis cycle. We also hold all subsystem meetings, either everyone together or in common areas of influence. So if we're talking about chassis, we were also talking about the deployer, which basically they need to interact more. Or if we were talking about the Raspberry Pi and the operating system, we were meeting with the people that was responsible for the software at the same time. We also created some focus on several critical needs first. So we knew that we had like 100 things to fix, but we focused on the critical ones and we just neglect the other ones for the time being until we fix the critical ones. We instead of working in a balloon hardware, in a flight hardware, we focused on the balloon first. So and then it give time to assess the components for flight heritage and for flight hardware that was requested. We increased a lot the internal communication. So we were doing meetings like daily, depending on the critical assessment, or at least like every week, everyone was meeting. But and then of course I was imposing explicit objectives and deadlines for individuals instead of teams. So basically I was assigning individually, like, hey, you need to deliver this by tomorrow or within 2 days or something like that. So here is one of the prototyping tests that we did, one of the first ones successful, where we can see the boom deploys itself on the first 3D printed model with some different approaches for this hardware. Although we were also using Raspberry Pi, and some capacitor with micron wire and fishing wire mechanism to release the boom. This is the second one test where we test the satellite under anti-gravity force, so it's going to release upward, and it's actually making Ben Shaker. He was not expecting that, but we can see that a lot of like electronics was needed, and also it is important to note all these voltage requirements and power requirements for the mission itself. So we were actually building software, building hardware, and designing the prototypes for the releasing the boom at the same time in a vicious cycle of rapid prototyping. So basically for block one, our changes were that cameras were fixed inside so that we don't need to work out the door mechanism. So we basically put it inside here. And the way that we did this was we substitute the Raspberry Pi B for an A, and we flipped 90 degrees. And then the mechanism, we flipped 100 degrees and put it upside down, upside. So because this upside part of the ThinSat is bigger than the lower side. So basically that's how we did it. So, and then on the door for the boom itself, we simply did not use the door itself. So we basically, we can see here, there's a little, the contraption itself has a little piece exposed here on the door, so the door cannot can prevent the boom to go in, but cannot prevent to go out. So basically, we set this to be free. It was also a risk for the mission itself to have a hatch on the door itself that could prevent the mechanism to be deployed. So instead of using one single stationary position, we decided to go with 5 outer rollers. So these rollers, they're all based on bearings, but they try to prevent in more positions the spool from blooming, so the boom for blooming outward. It was interesting because we started with 8 rollers, and then we actually saw that 8 was too much. It added too much friction to the system itself, so created a difficulty for the boom to be released. So we optimized that for a number of 5. Yeah, and so we also created the breakout board and the burning wire board adapted from the RockSat team, which is a Virginia Tech rocket team here. An encoder substituted the magnetic mechanism, so we also decided to not use a magnetic. It seemed to be too much for it, and then we had a lot of like options for encoders, optical encoders. There was a lot of springs inside the spool, and we just removed all that, and we just put a solid shaft in the spool itself. And then here we can see some renders from this design. So here's the optical encoder that reads the shaft movement. And also here we can see the amount of like electronics that was needed to be inside to make all this work. This is the final version. This was ready to go space balloon flight. This was our balloon flight hardware. So basically all the software was done, the Raspberry Pi was fast, the sensors, everything was working properly. And this was like around the August of 2019. And then hopefully this would go into balloon flight where we can get more information from the design and then retrofit for a space hardware. However, this did not occur because when we said we're ready to go for a balloon flight and we started to talk about integrating with the NSL bus, we were completely over all the requirements for power. So basically what happened here, you can see here on the end that we were monitoring how many voltages and currents we needed. but the ThinsSat didn't had yet talked to us about having larger requirements for current in their ThinsSat. So basically, the ThinsSat never had any payload that required a lot of power. So when we said like, oh, we need 500 milliamps of power, they said like, oh, we cannot provide that. And what was worse from that is that on their program, they only allow us to be powered on 10 minutes every hour. So we were afraid that we could not like even charge the capacitor to release the nichrome wire, to burn the finishing wire and release the boom. So this was like, okay, we need to reevaluate all our design from scratch one. So basically we missed this 2019 balloon flight, and we went back to redesigning the board, the ThickSat. So that leads to block 2. So in order to, the first thing that we knew is that we couldn't use the Raspberry Pi anymore, since only the Raspberry Pi itself requires around 300 milliamps of power to be idle on. So we said like, okay, we need to build our own PCB, and that will take time, but we need to do it. There is no solution from there. We also didn't know how we're going to use as an operating system, although since we all came from BCC, we were very familiar with FreeRTOS and C++, so we can actually use it, but it was too complex for a simple mission as the ThickSat. So we just created a TBD here so we could evaluate a little bit better. We also decided to try with NSL to show them that if they approve a 4-piece-wise chassis, it will be way cheaper, way easier to manufacture the chassis. We also introduced in our process and evaluation step, where every major design that we did, we actually talked with them, so they could like say like, yeah, we're okay with that, or something like that. Our hopes were for the balloon to fly the balloon first with Thane. So actually, we started making sure that all the components that we had was going to be space gridded. So we introduced a lot of like testing in TVAX and for the components in our process itself. Okay, so we did a reorganization on our team. So basically now we had a few more people, but basically there was a whole PCB and software development going on here. Seth was not available anymore, so actually I took the lead here. And then Seth just came into helping us on the image compression. And everything else kind of like became the same, except that I pushed Rob and Bryce to try to execute the TVAC test as soon as possible for each component. And we also had a little help from Stephen Noel in this moment for helping us with documentation and systems integration, as he was the expert on the field. So, okay, so let's talk about chassis. So chassis, the new project for chassis was to develop a 4-piece-wise chassis. This will be much easier to manufacture. There was like a lot more possibilities to manufacture the chassis, as it needed a 5-tau precision for the manufacturing. We also created a little bit of like some extra things on this chassis. So created sliding payload rails. So we can see here on the second one. So when you push the payload in the chassis, it doesn't go in a degree or magnitude wrongly. So it goes exactly on the correct position. And there's also a stopper here, so it doesn't go too much or too low on the correct position. We also created a PCB stand on the chassis, so the PCB is mounted on the chassis. And we also comply to all the NSL ThinSat version 2020, which includes all this opening diagnostic ports here where they can plug in. Okay, I'm back. And all these side screws here that we can see here on the little screws here, 1, 2, 3, and these are where the ThinSat bus is going to be screwed and contacted. So it's no longer a 1T, 5T, but it's a 6T piecewise where the NSL ThinSat is just going to mount on the side. Okay. Okay. So then we also increased a lot more stuff. So just to measure constraints on the 1 amp, so we basically decided to go, okay, so we don't need 2 cameras. We're not going to do a stereoscopic imaging for this mission. We're just going to replace with 1 camera. We also, we're going to, instead of using Raspberry Pi, we're going to use a PCB, and we decided to go with the STM32 Cortex M4 microchip, which gives us the opportunity to use MicroPython on it. And it was STM32 is a well-established microprocessor. We couldn't use the Hercules, which is a different development because the Hercules uses 150 milliamps in idle, where the STM32 only uses around 50 milliamps of power in audio. There was a requirement from NSL that we implemented. We implemented the side plates here to contain the bearings, so the bearings would not move if there was some vibration. Both side plates were in aluminum, and they were also anodized. So all the breakout board that required capacitors and using the nichrome wires, mainly all the necessity of using nichrome wire, we just decided to go with a servo unit. So servo unit is just a pulse width modular unit that we can manipulate the arm. And then we can see here on the spool, it has these grooves. So we spooled, we put the tape, we spooled we spool in the tape, and then at the perfect position, the arm goes in and holds the spool. And then when we activate the pulse width module on the unit, the arm moves away and the spool is free to release the spool. So this gave us like no requirement to have capacitors or to charge some kind of like voltage to burn the nichrome wire. There was also some compression techniques that we Seth developed where he could compress a whole image into 28 bytes. So basically he developed this edge detection technique that we can now use to compress a whole six kilobyte image into a 28 byte packet. I can talk a little bit more if you have questions. I can go back here on how that works. And we also, with that, we started to think about rooms, so where we can prioritize and estimate like 4 to 5 batteries and where we could put all these batteries. So about materials and manufacturing. So one of the things that was pretty, I think it occurred naturally because the 3D printing ultimately was so expensive and hard to find someone who has the printing to do it, that actually it came naturally a solution to buy Ultim plates for 50, 60 bucks, and then we could CNC them in a shape and form that we needed. That's basically what we did to substitute the Ultim parts that we were expecting to 3D printed them to have the possibility to rapid prototyping them. The other thing is that there was a decision on using the rollers as polycarbon, and also, yeah, because of their density and their the space requirement grading for doing that. This is an actual picture of the satellite. This is the 3D printed, and we can see here that the Ultim has this kind of like amber color. The black ones are the polycarbon. And of course, the aluminum plates were CNC and then anodized with the chassis. So if we talk about the customized PCB, I think that was the most challenging part of the project itself, because we started this from scratch. We actually never had the opportunity to have a PCB course, especially in the aerospace department. But after 5 revisions, we kind of like started to getting it to work. And then, so we also developed a breakout board that was easier to connect with our board. So the ThinSat board comes with a DF2L connector, and that was super hard because it was so tiny and so fragile to use it multiple times. So we actually break out to a DF13 connector, and then our board uses a DF13 connector to communicate with the ThinSat. And the ThinSat revision E, the ThickSat revision E PCB now has the possibility of provide services for an IMU SD card camera slot that we use. We also use one PWM IO slot, and we have also extra IO pinouts. You can flash the microprocessor through JTAG or SWO. It has a USB port, and it has also an extra of 16 megabyte FRAM. And like I said, uses the Cortex-4 microprocessor. So talking about MicroPython. So MicroPython is a good replacement for FreeRTOS if you're using a spacecraft that does not do too many things. Like the ThinSat gives all the avionics that we needed to transmit, communicate, and provide power that we don't need to worry about. So actually, we were just caring about the mission itself, which is releasing the boom and making sure that we take some sensor data about it, and then we format it in some way to transmit. So we don't need too much computational power to do that or complexity to do that. So we went to a simple solution. MicroPython is an amazing opportunity because you can actually just code Python scripts on it. And I think most of the students, they would prefer to go directly to Python. There are some caveats, of course, because since we're using the Python microprocessors, the flash memory provided by the microprocessor is so tiny that they do not allow MicroPython to have cool libraries like SciPy or other ones. So basically, it is a very raw-based, lower-level Python that you can use. However, you have all the needs that usually we do to communicate with sensors and other PCB boards, which it's listed here. I just want to also note that the MicroPython is an open source OS, and actually it required us to do our own customized build because our PCB layout had a pinout that was different from the pinout that was defined in a global variable inside MicroPython. We kind of like needed to change that and rebuild the MicroPython for ourselves. And that proved to be a very easy process. In the image here, we show the discovery board with the STM32 that we used to, while the PCB was not ready, we used to develop all the system processing and the flat set test. And here on the flight unit, a couple hours before delivering, we connect the spacecraft with just using a USB cord, and that pops up in the Windows machine as a flash drive where you can access directly the main PY file. Okay, so about the power and extra batteries. So as we said before, we needed room to put all the 4 or 5 batteries that we needed. So basically the chassis was great because we could put the 2 batteries beneath the PCB. On the side here around the sensors, we could put 2 batteries. And on the other side, since the ThinSat board was going to be touching this side, it needed to be thinner. So actually we split the cell of the battery into 2 thinner batteries, and then we slide one side of each other here on the other side. There was one thing that I wanted to talk here. Yeah, well, it's okay. So we can see, yeah. No, that's fine. Yeah, that was it. Okay. in the end, all the components and PCBs working together were above the 100 milliamps, but they were not like around 1 amp or 500 milliamps idle. Like a maximum usage of all the components together was around 120 milliamps, which we could now ask NSL to take out the constraint on the current, so we can ask them to stabilize the voltage on all the channels. So about data, just wanted to say that we are using 2 sensors to confirm the mission. One is the optical encoder that we're using on the shaft to confirm that the shaft is unspooling or spooling in any direction. So that's why the optical encoder is a good solution. And we also use a camera to take an image about from the deployment itself. So 2 things here are important. The first of all is that the optical encoder gives us a sequence of 2 bits. And since we were very short on how much bytes we could transmit, we actually concatenate all the bits in a big string. And then we sliced into 8 bits and created bytes for each 8 bits of encoder data. So that basically we are compressing by a factor of 4 of the encoder data itself, which gives us about 2,000 measurements for only 500 bytes. The image though, we decided not to go with any compressing techniques, because in all our research, even if we lose packets and we're using a lossless image compression like SLIF, we could not recreate image by puzzling back the packets. So there is a lot of work that was done by Seth and his team on that. So we actually understood that was a risk for the mission. So basically we just said like, okay, let's lower the resolution of the image itself and make sure that we track each piece of the puzzle. So even if we receive an image and some packets were missing, the image itself will not deteriorate, but we're going to have some pixels that is green. That's it. And if we repeat the mission process multiple times, as we call iterations, we can then create a composite of image over image, where those pixels that were missing now, they can be probably delivered in a different iteration process. So it is expected that we can execute each iteration at about an hour. So at a 10-minute for transmitting all the encoder data and a 50-minute to transmit all the image data. And that is very interesting, because if you have a orbital period of 90 minutes and you have a iteration for the mission of 1 hour, that means that half of your iterations will be in daylight and half your iterations will be in night, in dark light. So you can have, if all the iterations come along, we will have data for both in the same number. So that's one thing. So about packet transmission, so since we're doing repuzzling all the packets that we were receiving, and we don't have confirmation from Globalstar that all the packets will be received, we need to keep track of which packet number is it, and also which sensor data is it about, so we can receive an encoder data and then receive a packet from an image and then receive back an encoder data. So since we're receiving all this mixed it up, we decided to use 2 bytes from all our packets to identify what is the sensor and iteration, and also the number of the packet itself. And all the remaining 33 bytes is actually data. The other thing that we implemented about the software is that is a persistent to power cycle. So if the spacecraft loses power and reboot itself, it has the ability to understand where, which sensor and which packet it was power cycle, so it can resume exactly at that position. So we don't transmit multiple, we don't double transmit any data, or we don't resume from the beginning. And then we had a plan to be delivering by spring 2020, but COVID came. So basically they moved all the launches to NG15, which was a little bit nice and a little bit sad because now we had a little more time to build up and create more risk assessment on our spacecraft. But at the same time, we kind of like lost the ability to do a balloon test. So we actually built the spacecraft directly to launch into space. So future recommendations, I recommend also reading the VCC series CubeSat mission challenges and lessons learned that was published last year, which has a lot of experience from the VCC delivery and building process of the spacecraft itself. I'm not going to go through these recommendations, but there are some recommendations here there that I think it adds up with all the recommendations that we're doing for the ThickSat. So recommendations that we're doing for the ThickSat, so build partnerships. So if you have an institution and you don't have the exactly manufacturing skills or 3D printed equipment or a vacuum facility to use, you can always partner with some other institution that has it. And one thing that I've learned from this process that having partnerships also it creates a lot of like opportunities to know people, and they are always willing to help. The other thing is exercise your partners. Most of the time, you'll feel that the requirement given by the partner is a requirement that's not going to change, but sometimes they're just requirements that are there because they need to be there, and they are flexible enough. So make sure you exercise those requirements with your partners so they can say like, no, we can change that requirement to make room for some design struggle that you're going through. Make sure that you keep all the requirements for your mission managed and all the requirements for your partners managed. So make sure that all the versions of the documents that are going through each partner is the last one. So you don't build up some chassis based on a previous version of a file, for example. Also, make sure that you constantly question your design for simplicity. I know that most of the students have the tendency to add complexity to make your project more beautiful in terms of like engineering complexity. But when we build actually the mission itself, the more complex it is, the more risk you will have for the mission success. So make sure you go into a simplified mode once you receive the spacecraft to actually deliver it. So also exercise rapid prototyping. It's great for making sure that all those like crucial design specs that you're doing are confirmed or evaluated correctly. So build a test and come back, and rapid prototyping is good for that. 3D printing is amazing because it's very cheap. You can build many times. Make sure that you do literature review. So go to other projects. Like there was a moment where I think it was summer of this year where I started to go through the literature review of the missions. I saw a lot of other institutions trying to do the same thing with different solutions, and that was very interesting. And also in the last one is the ultimate material. Usually we'd go for 3D printing if it is plastic, but you can actually buy the plastic plates and CNC, and it proved to be cheaper and easier to do it. And then just the final thing is that some publications, just to make sure that we give some credits, is that Derek did a great publication for SmallSat on the chassis itself. I recommend going there and reading his paper on it. It has all the details on all his interactions on how to find the best chassis possible for the ThinsAt program. And then Rob also did in the same conference an amazing paper on the boom release mechanism, where he proves the amount of rollers that are required to have to optimize the release of the boom. So I also recommend to go and check his paper. And I think that's it. I would like to thank a lot for all the students that have participated in this project. Here are all the names. And I'm opening to questions.
All right. Well, thank you so much, Gustavo. Yeah, very good. Yeah, I was going to ask. I'll start maybe just a comment that's pretty exciting. I could see that the chassis, that making that custom thing, that's a huge win for this, and especially for the VT team. But as well, has there been anything on putting that that custom PCB for kind of microcontroller OS out there as well?
Yeah, so the STM32 can receive as much different options for operating system. We can actually put FreeRTOS or other RTOS that are there, which is kind of like safer that we know about. It's very, the STM32 is very versatile. We chose to use MicroPython because we wanted to have the simplest option and easier way so we could focus on other areas for the satellite itself.
And I guess it's not as much of a question on the OS, but just the hardware component of that, of getting that microchip integrated into like a ThinSat kind of form factor.
Yeah, so building the PCBs. So when we started doing the PCB, which was revision 8, it took us more than 15 times to develop the expertise of putting the microchip there and cooking it and making sure that all the components, to actually have the first time that we actually see the microchip turn on. So building those PCBs are somewhat an expertise that we had the opportunity now to do it inside Space AVT that we didn't have before, at least in the student level. And now it became something that we are very familiar with. It's kind of like riding a bicycle. So it's kind of like before it's super hard, and then eventually it's like, okay, that's easy. So I think now we're in the verge that we as an institution and Space AVT and the Human Center can provide the PCBs already assembled and ready to use for multiple missions around Virginia Tech or even outside the institution.
Okay, yeah, I think it's, I was getting at it basically, is that something that to market, or that, maybe other universities or companies will kind of look to us for, but I don't want to dominate the questions. Certainly other people
Sure.
can ask. So.
I don't have a question, but I just have the comment that this is very impressive stuff. Well done.
Thank you.
Where do you see this going? What's it going to look like 2 or 3 years from now?
I don't know. Like, I think this mission is to be in space like for a maximum of a month, and then eventually it's going to burn out in the atmosphere. We expect the mission to endure its batteries, if it is not chargeable, by 24 hours, 21 hours, which will give us like a 15, 16 images. But I think this mission proves itself in terms of PCB and chassis in such a way that enables a variety of other missions to come along. Since the Thinsat program is way cheaper than doing a CubeSat and way faster, since we don't need to do avionics, so we can actually put up to speed a lot of technology that we want to test in space under this projects in a more off-the-shelf way. So I think that's one of the things that Dr. Black wishes to do with this, as a deliverable from this mission forward.
Yeah, and certainly too, I was going to say congrats on getting to this stage. And what is the, I don't think you said it's for a launch in next year, but what's the current, I guess, steps, or, where is it at, kind of now?
Yeah, so we are now at the week that we are all like in fear because it's gonna go into the stand to a vibes test. So as soon as this is released from the vibes test, then it's gonna go directly to Wallops to then sit there until the rocket is launched, and then we're gonna see hopefully the packets coming through their dashboard.
All right, well, I guess we'll all certainly cross our fingers that it survives the vibe test this week.
Yeah.
Any other questions or comments? I think I see most of the participants are probably on this slide that you have here, so maybe that's why things are more quiet today. Going once, twice. All right, well, thank you so much again. Thanks. Hopefully everybody can thank, has a chance at some point to thank Gustavo, and certainly congratulate him and the rest of the team here on a job well done, and we'll hopefully be looking forward to some good news here in the next week or two. And otherwise too, is just a closing note on the Space of VT seminars. I might grab the screen from you. If I can see. Let's see, which one do I want to share? This one. So next week we have one of our joint seminars with the Center for Geospace Storms, or with CGS. And that one will be actually at 3 o'clock, not at 2 o'clock. But I'll pass along information for those. And then otherwise, we only have one more left in the for the semester, and it will either be the 2nd or the 9th year. That one's still TBD. So thanks everybody for joining for this week. And again, thank you, Gustavo, for sharing on the ThickSat program. And we'll be hoping for some good news.